I work at NASA's Jet Propulsion Laboratory in Southern California, just outside of Los Angeles, and I work on exoplanets. So the ultimate goal of finding life in the galaxy. So like in that awesome intro, I work here at NASA's Jet Propulsion Lab outside of LA and SoCal. This is a picture of JPL here in northern Pasadena. You can tell this photo is from thousands of years ago because this is obviously when LA used to have water around it. And I live in this little building, or I guess live is still appropriate. And this little building right here on JPL, and I work on exoplanets. And working at NASA's and NASA in general, but also JPL has always been a dream of mine. Ever since I was a little kid, I've loved NASA and astronomy and space. And here's actually a picture of me as a little kid at the Kennedy Space Center, visiting the visitor center there, meeting my hero, the astronaut. And tons of people ask me all the time, you know, Rob, you love space, you are a giant NASA nerd, you love Star Wars and everything. I'm wearing a James Webb Space Telescope shirt, for God's sakes, folks. I'm a giant nerd. People ask me all the time, you know, do you ever want to be an astronaut? And the quick and easy answer is absolutely no. And that's because I'm deathly afraid of heights. That's sort of a job requirement for being an astronaut. So I am what I think is the next best thing. I'm an exoplanet astronomer. So let's unpack what this means. Well, an exoplanet is just short for extrasolar planet, where extrasolar means anything beyond or outside of our own solar system. And planet, hopefully you all know what that is. So an exoplanet is any planet outside of our own solar system. And then I'm an astronomer, probably what we do. It's that someone who stares at the sky, or more likely their computer, for way too long. I spend a lot of time actually working on my most important tool is arguably my laptop, working on various things here at JPL, whether it's working on missions like the Nancy Grace Roman Space Telescope, working on instrumentation, running a citizen science project. And a lot of that work actually happens, most of my day is spent on my laptop. And I do get some observing it, but it's honestly few and far in between. The data runs happen only a few times a year, and then I'll spend a lot of time analyzing and reducing the data on my laptop and making interpretations about what it means for a planet's physics or its atmosphere or its dynamics. But as an exoplanet astronomer at JPL, what I'm really ultimately looking forward to doing is helping answer that age-old question, are we alone in the universe? Again, giant Star Wars nerd. And I want to ride the Millennium Falcon. But in order to ride it, I have to know where it's parked in its hangar, right? And by working on exoplanets, I'm helping, at least I hope so, to directly answer this question, if we're alone in the universe, if there's alien life out there. And by looking for planets that could potentially host life on their surface. And actually, the idea or the field of exoplanet astronomy is actually one of the newest fields in astronomy. It's only been around for the last 20 or 30 years ago. We discovered the first exoplanet in the mid-90s. And despite this being one of the newest and one of the fastest growing fields in astronomy, the idea of alien life or exoplanets has actually been around for hundreds of years. So for example, Giordano Bruno, he's that guy at the top right, looks kind of like Emperor Palpatine. He actually postulated back in the 16th century that there were other worlds out there that could be hosting life. And then Isaac Newton, the dude in the bottom right, you know, he's the famous discoverer of fig Newtons. He said in his book where he talked about the theory of gravity in Principia, he said, and if the fixed stars are the centers of similar systems, they will all be constructed to a similar design. In other words, when we go into the night sky, when we look at all those hundreds of thousands of stars in the sky, it stands to reason that those stars also have planets orbiting around them. Just like we have the 8 planets, 8 because Pluto's on a planet, the 8 planets orbiting around our own sun, perhaps there are other planets out there orbiting around those stars as well. And we now know, hundreds of years later, that these 2 dead guys are absolutely correct. That when we know how to look, where to look, when to look, as we get better technological advancements such as digital cameras and larger telescopes, we have been discovering exoplanets at almost an exponentially increasing rate. This chart I made about a year or two ago, and it's actually already out of date by 1,000. So at the time, 2 years ago, we knew of over 4,000 exoplanets, but today we know of over 5,000. And thanks to missions and efforts by groups such as NASA and some of their space-based telescopes, we now know that there are at least as many planets as there are stars in the sky. So in other words, planets are out there. They exist, but also they're everywhere. And when there's planets, the next question is there also life? So how do we find life? Well, we can break it down into, honestly, this three-step method. We can find an exoplanet. You have to find out where they're living. You have to then determine if that planet has the conditions necessary to support life. And then the hardest and the most important of this question is finding that life. Just because a planet could support life doesn't guarantee that it does have it on its surface. So let's look into quickly some ways that we can find an exoplanet. Well, as you might be aware, it's actually really difficult to do. There's a huge problem in that they're so far away that we typically only see that the star is orbiting. And that's because the star is so much brighter than the planet itself. So we either need a way to block out the star, to basically remove its signal so you can then resolve the signal of the planet orbiting around it, or we need other methods to infer that the planet is there. So we actually have a variety of different methods that we use to find exoplanets, but the three I'll be focusing on today are the radial velocity, the transit, and the direct imaging techniques. Radial velocity and transits have arguably given us the most information about the most number of planets to date. And direct imaging, I work on a direct imaging mission, so I'm contractually obligated to tell you guys about it. So a little patience on that, please. So let's look at the radial velocity method. This is called the Doppler shift or the wobble method. And what happens is when you have a planet orbiting around the star exerts a gravitational tug or a pull on the planet, and that causes the planet to orbit around the star. But the planet itself is also inducing a tug on the host star. So as much as the planet is being tugged by the host star, the planet also wobbles its host star back and forth. And we can actually observe this wobble from the Earth. And then by looking at the size of the wobble and how quickly it happens, we can actually back out that one, a planet exists there, but also how massive or how large the planet is that is inducing that wobble. So we can actually use this method to not only discover planets, but also to measure how much they effectively weigh. Another method that we use a lot is called the transit method. And what this does is this measures and looks for planets passing in front of their star. So let's pretend we're looking at a random star in the sky. If we're lucky, that star will have a planet around it. And if we're even luckier, if it's in the right geometry, that planet will occasionally pass in front of the host star, blocking out the star's light and causing the star to appear to slightly dim. And that size of the dip in brightness, how much the host star dims, directly tells us how big the planet is relative to its host star. The more light that's blocked out by the planet indicates that we're looking at a larger planet. Smaller the dip in brightness of the host star, smaller planet. And at best, these signals typically are only about 1 to 3% for a large Jupiter-like planet around a solar-sized star, one that's the size of our own sun. But this method is extremely important because this allows us to directly measure how big the planet is, its radius. And as I'll talk about a little bit more in my talk a little bit later, is this does allow us to study the atmospheres of these planets. When the planet passes in front of the star, not only does the planet's optically thick or blocks out lots of light, its disk block out a lot of light, but also the thin little slice of atmosphere around the planet also absorbs some of the star's light. And by looking for that signal of how the atmosphere impacts our observations of the star's light, we can actually directly characterize the planet's atmosphere. I'll talk more about this in detail a little bit later. But the transit method has been used to discover 3,000, probably actually more towards 4,000 of the currently known 5,000 transiting exoplanets. And right, so some really great advantages of the transit method is relatively cheap. People have been able to use telescopes as small as about 6 inches or 10 centimeters. Actually, 4 inches, I think, is the smallest scope I've seen that can contribute and take transit observations. I also saw online someone used just a DSLR camera, a digital camera, to observe a transit as well. And this gives us the size of the planet. But there are some disadvantages of this method, and you're biased towards longer or larger planets. The bigger the planet, the more light it blocks out when it passes in front of the star, and the larger signal it induces. So it's easier to find large planets around stars. So it can be biased observationally as well. But NASA missions and NASA efforts, along with ground-based telescopes and surveys as well, have done amazing work on discovering new transiting exoplanets. One mission that's currently up is NASA's Transiting Exoplanet Survey Satellite, or TESS. And here's a picture of TESS right here. TESS was launched a few years ago, and TESS is predicted to discover up to an additional 10,000 new transiting exoplanets. So again, today we know of 5,000. TESS will potentially triple that number by the end of its mission lifetime. And TESS is a full sky survey, so it has these 4 onboard cameras that take slice images or pictures of slices of the sky. And then over its mission lifetime, it slowly rotates around the entire sky, looking for the tiny dip in the host star's brightness, indicating a new exoplanet out there. And right now there are thousands of candidates that TESS has discovered, and at least tens, if not hundreds of planets that TESS has been confirmed as real planetary detections. So you might be saying, Rob, we already have 5,000 planets. What's an extra 10,000? What's the big deal? Well, it's because we need TESS to help us identify planets that we can then follow up with other large NASA missions and European Space Agency missions as well. So, for example, the Hubble Space Telescope is currently observing exoplanets using the transit method to characterize their atmospheres and figure out if there's water in there or if there's hazes or clouds. James Webb just came online a few months ago, nearly a year ago now, good Lord, has been doing amazing, impactful science. It seems like almost every week or every other week, there's a new press release about some impactful new science coming out of James Webb of making new discoveries on exoplanet atmospheres. Ariel, which is a European Space Agency mission, will be dedicated to looking and characterizing exoplanets. And it's predicted to look at up to 1,000 exoplanets. And I would argue beyond that as well, it's imperative and that the transit method is actually here to stay. That future NASA and European Space Agency missions will continue to observe exoplanets using the transit method to characterize their atmospheres as well. So to really help these projects achieve full success is by giving them many thousands of targets that we can then select from and then do impactful science with. So that's a really super quick overview on both the radial velocity and the transit method. And actually, you can also help out, make your own observations of transiting exoplanets. I'll give a slightly quick plug here, and if there's more time, I can come back to this later if there's any interest, if you want to ask questions about it. But we're going to be launching next month a citizen science project called Exoplanet Watch. We actually have a very real need where we need folks like any of you on the line to either conduct their own observations using their own telescopes, or you can use some data that we have on robotic telescopes, analyze that data, and help us use these large resources, Hubble, James Webb, Ariel, a lot more efficiently and effectively by helping us make better predictions of when these transit events were to occur. And I'll be making hopefully some press releases about this next month. So if you don't have your own telescope, in a few weeks, you can participate fully in this project. But if you're an amateur astronomer who's on the line, we would absolutely love you to participate right now. You can start making observations tonight and reduce them and analyze them and make impactful science-grade observations just in a few minutes. So you can contact us there at that website or email address. I usually can't remember it, so I just Google NASA Exoplanet Watch, and hopefully we're the first link that pops up there. But also I can answer more questions afterwards as well. All right, so I'll get off my soapbox there for a minute. That's the two of the main ways we currently find and characterize exoplanets. The radial velocity method, we're looking for that wobble of the host star, and that tells us how much the planet weighs, its mass. Then the transit method, when the planet passes in front of its host star, blocks out the star's light, causes the star to slightly dim, and that tells us how big that planet is relative to its host star. Another method that I work on here at lab is the direct imaging method. And as you probably figured out in the very inventive title, is literally taking photographs of exoplanets. But there's a big problem, which I alluded to earlier in my talk, and it's really hard to see these planets through the glare of their host star. So let's try to make it a lot easier for us to do. Let's take a large planet, like a Jupiter-sized planet. Let's put it around a sun-like star. Let's also have the planet heated up a lot, so it's actually glowing from its own heat, its own light. Well, that hot exo-Jupiter is still 1,000,000 times fainter than its host star. That's like looking for the light of a firefly around a lighthouse, and you're on the East Coast observing on the West Coast. So you're observing across the entire US. That's all well and good. Looking at hot exo-Jupiters is cool. But what we really want to do, at least in my opinion, is we want to find alien life. We want to find and observe and characterize other Earth-like exoplanets. So if we take that same Earth-like exoplanet, put it around a same star, just like our own sun, that planet is 10 billion times fainter than its host star. That's like looking for one bioluminescent alga around that same lighthouse on the other side of the US. So hundreds of miles away, if not thousands of miles away. It's a very, very difficult thing to do. So how can we cut down the light or block out the light of the host star to then resolve the planet's light alone? Well, some of you who were fortunate enough to see the total solar eclipse or even a partial solar eclipse, you'll remember that when the moon passed in front of the sun, it caused the sky to get a lot darker, and it allowed you to see not only the outer levels and portions of the sun, the corona, but also you can see actually stars in the sky as well that are around the sun. And we just can't see them during the day because the sun outshines their light. So if there is a way we could sort of simulate a solar eclipse by maybe making a piece of hardware that can block out that star's light, perhaps we can then resolve the light of an exoplanet. And this is literally what we do today. This technology is called chronograph. And this was actually first built and designed to simulate solar eclipses from the ground because astronomers got impatient. We didn't want to wait years between one solar eclipse to the next. So they literally built this little disc called a chronograph, this instrument that would then pass in front of the sun and simulate a solar eclipse. And now today, hundreds of years later, that has been adapted to allow us to directly image exoplanets. And I have this really cool video from Goddard about it.
A coronagraph is a way to see distant planets hidden by the glare of the star they orbit. The coronagraph reduces the light coming directly from the star to separate it from the light reflected by the planet. The Nancy Grace Roman Space Telescope's coronagraph doesn't block the star's light with an opaque disk, as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover, distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects distortions in the light beam. As the mirrors deform, the blobs of light slowly begin to disappear, revealing brighter planets. Further adjustment brings fainter planets into view. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, the Roman Space Telescope will provide the first look at individual planets in star systems that might be similar to our own.
I'll be talking more about the Nancy Grace Roman Space Telescope in a little bit, but that's basically how direct imaging works through a lot of magic. But literally, it's making hardware that can block out the light from the star, and then any residual starlight that sort of refracts or bends around that original mask, and then uses some fancy computer processing at the end of the day to further amplify the signal from the planet and further suppress the light from the host star. And direct imaging has been used very successfully on the ground. So what I'm showing here is actually an animation of some direct imaging observations from the Gemini telescope here on the Earth. And this data was taken over about 7 years. At the center of this image is where the star would normally be, but most of the star's light is blocked out due to the coronagraph disk itself, and also using deformable mirrors to further remove some of the stellar signal. And some of the star's light still gets through, which is why you see this pattern right here. But what you can see, though, is these 4 little specks of light. These are each extrasolar planets. These are exoplanets orbiting around their host star. And we're observing this extrasolar solar system over 7 years. So we can actually observe in real time as these planets are orbiting around the host star, which is absolutely incredible. My background prior to joining this project is transits. I would observe when the planet passes in front of the star, blocks out the star's light. I could never directly see my planet that I was studying. I'd have to infer its existence. With direct imaging, you can take photographs of the planet you're actually studying. It's just mind-blowing to me. And honestly, I've been jealous for years. So I'm really happy and fortunate that I get to be part of this mission that uses direct imaging technology. All right, so now what? Okay, so we've discovered over 4,000, now today actually over 5,000 exoplanets. And this used to be a big deal. You know, I remember in the late 90s, early 2000s, I would have a phone app and it would go off, you know, once every few months, and it would be a big deal. They discovered a new exoplanet. And now today it's kind of blasé. People are like, all right, cool. Yeah, we know they're everywhere. Who cares? And it's now that's because the field is starting to make that transition from planet discovery now to planet characterization, and has been so for the last 10 to 20 years. So how do we take this next step from planet detection to now planet characterization, to saying not only that a planet exists there, but also what molecules are in the planet's atmosphere, what temperature is the planet's atmosphere? For example, does it even have an atmosphere? And if it does have an atmosphere, you know, what molecules are present in its atmosphere? Does it have water, methane, carbon dioxide, carbon monoxide? If it does have these molecules, could it support life? Does it have an environment that will be acceptable for life to form? And if so, does it actually have life on its surface? So this brings us to our next step. We went from planet discovery to now we have to characterize that planet to figure out if it could support life on its surface. And one way we use to sort of whittle down our target list, we know of 5,000 planets today, but how do we prioritize what planets we study to look that are potentially habitable, that could have life on their surface? Well, we use something called the habitable zone. And this is sometimes called the Goldilocks zone. And this is the zone where liquid water can exist on a planet's surface. And this is important because all life, as far as we know it, requires liquid water to survive. If you look on the Earth, if you look in our own solar system, life, as far as we know today, only exists on the Earth. And when we look at all the life that does exist on the Earth, all life requires liquid water to survive. So yes, admittedly, it's using a very human and Earth-centric view of the universe and applying it from what we know on the Earth to the rest of the cosmos. But by looking at what we absolutely know today, life exists only in these conditions, we're using that to whittle down from our 5,000 planets to the tens of planets that could potentially host life. So by the habitable zone, what I mean is if we take if we look down on our solar system, we look at the sun, Mercury and Venus are a little bit too close to the sun. They're too hot, liquid water cannot survive. Mars similarly is too far away. But the Earth is just right. It's not too close, not too hot, not too far away, not too cold where liquid water can freeze out. Earth is just right where it has the conditions, it has liquid water on its surface that is necessary to power life. That's all well and good. This helps us estimate what planets are in the right location from their star to tell us something about potentially having water on their surface and might potentially be able to support life. But how do we take that next step and say definitively, yes, this planet has water on its surface or in its atmosphere? Well, to do that, we leverage something called Beer's Law. And I found this really, really great definition of Beer's Law on the internet. So let me read this out to you, to all of you. This is studying for a test or doing homework while beer is involved, making difficult classes such as physical chemistry more bearable. That's a great definition, and I definitely did that a lot in grad school. I studied lots of Beer's Law to help deal with my PhD program. But here's the real Beer's Law. And what it does is it describes the absorption and scattering of light out of a beam. So what this really means is, let's make a thought experiment. Let's set up a light bulb in our lab, and then let's put in front of the light bulb a chamber of gas, such as a chamber full of carbon dioxide. Now, if we put the light bulb there and put the box of CO2 in between us and the light bulb, if we looked on the other side of that box, out here, we would notice that that light bulb is slightly dimmer than it should be. And that's because the chamber of gas is absorbing some of that light and scattering it out, so it makes the light bulb look dimmer. But what we can actually do is we can use Beer's Law, this equation right here, to compare the light, how it does look, and compare it to what it should look like. And then just by using this equation, we can actually figure out what type of gas is in that chamber that's causing the absorption. So just by comparing the light bulb to how it should be, to how it actually looks, we can actually directly back out the composition of the gas, the absorbing medium in that chamber in our own lab, which is really handy because exoplanets, the nearest one to us, is 3 light years away, hundreds of millions of miles away from us. And we could still characterize exoplanets by leveraging and implementing Beer's Law. So, for example, if we're an astronomer and we're observing a yellow star, that yellow star would emit yellow light, and we'd see it as yellow. But if we put between us and that star like a giant gas cloud, like a nebula, that nebula has gases and dust inside of its atmosphere, inside the cloud itself. And what it does is it'll absorb some of that star's yellow light, and it causes the star to look slightly red. And then we can observe how the object does look like. That yellow star actually looks red to us, and compare it to what it should look like. It should look yellow. Then we can actually use Beer's Law to determine the composition of the absorber. We can actually use Beer's Law to figure out that there are certain molecules like hydrogen and helium inside that nebula. We can do the same thing for exoplanets. Let's pretend we have an exoplanet and we have one that still has some residual heat in the core of the exoplanet. Just like with our own Earth, we have that really hot liquid molten core. Other exoplanets also have hot molten cores as well that are emitting heat and light that's being radiated away from the core of that planet. And the outer layers of that planet are comparatively cool because the outer layers of the planet are simply farther away from the core, just like it's not boiling hot on the surface of the Earth, depending on where you live on the Earth. So what happens is that light, that heat that's radiated and emitted by the core of that planet starts to go through and travel through the relatively cooler layers of the planet's atmosphere. So that light that used to be yellow, bright, and hot is now comparatively cooler and reddened. And then astronomers, such as this random kid out here, can look at this signal of emitted light of this exoplanet, implement Beer's Law, and then say, hey, that planet has methane in its atmosphere. Same thing happens here in our own solar system, and it can actually apply this to exoplanets as well. In our own solar system, we have the yellow sun emitting yellow light. It'll hit a planet's atmosphere or its surface, such as the clouds of Jupiter. And due to the molecules in Jupiter's cloud bands, that yellow sunlight is reflected and slightly reddened as well. So then astronomers on the other side of that telescope can then say directly that there are clouds, methane clouds in Jupiter's atmosphere. And we can do the same exact thing for exoplanets. We can look at how exoplanets absorb, emit, and reflect the light from their host star to figure out exactly what they're made out of, thanks to Beer's law. So again, Beer's law is extremely powerful. It allows us to characterize an exoplanet's composition by observing how the planet emits, absorbs, and reflects light. So we can characterize things that are hundreds of millions of miles away without even having to travel there. So let's look at some real data. Here's actually a study that was published a few years ago where they took a ground-based Earth telescope and they observed 7 exoplanets here on this x-axis, on this y-axis. And they've taken a look at the light emitted by these exoplanets and they've spread it out into all the wavelengths. So they basically did what they did on the Dark Side of the Moon album cover by Pink Floyd. They have that white light coming in to a prism or that triangle piece of glass. On the other side comes out the rainbow. So they've taken that light that was emitted by these exoplanets, spread it out, and have now plotted that versus its wavelength. On this axis, they've aligned the planets so that the bottom is the coolest and at the top is the hottest of the planets. And on this axis is the wavelength of light. These are infrared passbands, wavelengths of light that is expected to show a lot of molecular signals. And by what that I mean is that if you see a bump and wiggle at these wavelengths, that indicates that that planet likely has water in its atmosphere. Similarly, if you see a bump and wiggle at these wavelengths, that means that methane is absorbing some of that light and inducing a signal in the spectrum of the planet. And we can actually determine if that planet has methane in its atmosphere. And out here, this is where carbon monoxide most strongly absorbs and reflects light. So some of you eagle-eyed folks out there might have noticed these lovely gaps in the data. And the reason for this is because these observations were taken from the ground. And this is actually where the Earth's atmosphere absorbs light as well. A lot of the molecules we're interested in discovering in these planets' atmospheres are the same molecules that are in the Earth's atmosphere. And the stupid Earth's atmosphere gets in the way all the time. There's annoying stuff like oxygen and water and carbon dioxide. And there's so much of it that it actually fully absorbs at these wavelengths and makes these wavelengths nearly completely inaccessible from the ground. So if you can't access these wavelengths from the ground, what do? Well, you go out into space. And the Hubble Space Telescope has been amazing. And this is one of the main reasons that folks love to use the Hubble Space Telescope, because not only does it have amazing, impeccable data quality, but it also gives us access to wavelengths of light that are typically inaccessible to us on the ground. And similarly, the James Webb Telescope, which was just launched about a year ago, started observations earlier this year, it's the next logical successor to these space-based missions. James Webb, just for comparison, the Hubble Space Telescope, its mirror diameter is about 2.5 meters, or about 8 feet across. James Webb is about 6.5 meters, so nearly 3 times larger, so about 20 to 25 feet across. So a human would roughly be maybe the size of 1 or 2 of these hexagonal mirrors. This telescope is so absolutely giant that it is larger than the nose cone fairing at the top of the rocket that it was put on and launched out into space, that it actually had to fold in on itself like origami in order to fit into its own rocket. This purple thing at the bottom is a heat shield, a solar shield, and this is the size of a tennis court. And this is just an amazingly giant piece of machinery. I was really lucky enough to see it out in Los Angeles and was out here doing some testing as well. And it was just mind-boggling how giant it is. And this is one of the main reasons we're so excited to be using James Webb today, is because it's so much larger than Hubble. So it can collect more particles of light. It can get us higher fidelity measurements. It can look at smaller and smaller signals due to its higher sensitivity. But also, James Webb has a lot more wavelength coverage than Hubble does. And that enables us, by looking at different wavelengths, we can start looking for other molecules in these exoplanet atmospheres. And then looking beyond James Webb, it's always helpful to look into the future, is a mission that's upcoming, that's launching in the mid-2020s, called the Roman Space Telescope. This is named after Nancy Grace Roman. She was NASA's first chief astronomer, and she's sometimes called the mother of the Hubble Space Telescope because she was one of the main folks that really championed the idea of a space-based observatory. So in her honor, NASA has named this telescope after her. And this is actually the size, the same mirror diameter as the Hubble Space Telescope, but it has a much larger field of view. But it also has a direct imaging instrument on board that I work on here at JPL, and that is the Roman chronograph. What the Roman chronograph will do will allow us to take this technology that's been demonstrated so very successfully with large 5-meter, 8-meter, 10-meter class telescopes, and for the first time demonstrate all this technology in space. And this will directly allow us to help us define the technology and the capabilities that we need to look for Earth-sized planets. So again, currently today, we are limited to looking at planets that are comparatively far away from their host star, that are big, that are bright, that have a bigger signal and easier to see. What Roman will allow us to do is start looking for true Jupiter analogs. Planets that are still Jupiter-sized, but are a lot cooler, a lot more temperate, so therefore they emit a lot less flux. They're also much closer to their host star. You might say, well, Rob, what's the big deal about actually directly imaging Jupiter-like exoplanets? That's because of where we want to be. Ultimately, we want to be able to directly image Earth-sized planets in Earth-like orbits, Earth-like distances, around solar or sun-like stars. Because if we can directly image these exoplanets, these Earth-like planets, we can start looking for signals that indicate that life could or does exist on their surface. But in order to get from where we currently are, large, big planets that are relatively young, that have a lot of leftover heat from they recently formed, to where we want to be, small planets that are close to their star, that have a smaller signal because they're so much dimmer and smaller and cooler, we need Roman chronograph to give us that stepping stone here in the middle to establish that these technologies do indeed work in space. They've only been shown really completely on the ground, and learning a lot of lessons on what we can then adapt and apply to the next generation of NASA missions that are explicitly built to look for Earth-like planets that are launching in the next 10 to 20 years, the next big NASA mission. So you might be asking yourself, why even bother with the ground? You know, space-based telescopes are absolutely amazing. You're not limited by Earth absorption. They're minimally impacted by sunlight. And the problem, though, is that everyone, rightly so, wants to get on Hubble and James Webb. And the reason why everyone wants to get on Hubble and James Webb is because it's above the Earth's atmosphere. We have access to a large wavelength of light. And everyone wants to get on these two amazing platforms to do their own science. And as such, it's very competitive to get time on these telescopes, and it's very limited the amount of time that you can get on these scopes. So that's not necessarily an issue, though, with ground-based telescopes. There are numerous, tens, if not hundreds of telescopes across the world that we can actually have access to. Of course, you have to deal with things like sunlight, like weather, like clouds, like rain, or also dealing with all the lovely systematic errors that occur on ground-based telescopes. Yet ground-based telescopes are still extremely important and helpful for answering a lot of these issues as well. I'm actually seeing in the chat from Gloria and Pete, they're saying, since we are heading back to the moon, is there a near future plan of building a moon-based telescope to avoid atmospheric issues? I would assume this would also provide easier future maintenance than space-based telescopes. So actually, moon-based telescopes is an idea that has been around for a long time, and many people have identified and suggested potential missions that could place a telescope on the moon. There are still a lot of technical issues with putting a telescope on the moon. And that is, for example, there's a lot of moon dust, and that can get into the optics of your telescope. Also, it's really, really expensive and technologically difficult currently to get a telescope out to the moon. We haven't been to the moon in the last 50 or 60 years, much less put a telescope on it. So is that huge technical limitation, or at least outstanding question of how do you get a telescope onto the moon? So currently, focusing mostly on these space-based missions. There's also other issues to take into account as well, as we're to install the moon on the telescope on the moon's surface, because some parts of the moon are illuminated about half the month as it goes through its cycles. So that is definitely stuff or ideas that people have been studying, and perhaps we'll see eventually a telescope installed permanently on the moon. It'll be cool to see. But today we have typically the space-based telescopes, Hubble, James Webb, soon Roman in the next few years. That's the next massive flagship they'll be launching after James Webb. And we have these tens or hundreds or thousands of telescopes here on the ground. And this is one of the reasons I'm helping commission this instrument called NESSY, which is at the Palomar Observatory. This is a telescope that was first commissioned in 1948 in between Los Angeles and San Diego. And for about 50 years, this was the world's largest fully steerable optical telescope. And it's a 5-meter telescope, or about 200 inches across. And we're able to use this very historic, significantly impactful telescope. It was built and commissioned 50 years before the first exoplanet was ever discovered. And we're able to now observe and characterize exoplanets just by throwing NESSY onto this telescope. And NESSY stands for the New Mexico Exoplanet Spectroscopic Survey Instrument. It was actually built by some folks at New Mexico Tech, and they are loaning it out to us at JPL. And it's now being commissioned right here at the 5-meter Hale telescope just outside of Escondido in Southern California. So I'll show you all a really cool picture that was taken of NESSY a few years ago. No, that's a mythical sea creature, sorry. Here is the actual instrument NESSY. For context, this is probably about 4 feet tall. And here is the instrument itself on its handling cart. And here's some of its computer hardware. And I'm doing some testing in one of the labs here at Palomar. And what NESSY does is it's actually installed at the top of the telescope. Normally, when you sort of think about the telescope, you have light coming in, hitting your primary mirror, then it's reflected to your secondary mirror at the top, the other end of the telescope, and then it's reflected again through a little hole to the instrument bay at the bottom. So you'll have your eyepieces or your cameras at the bottom or the back of the telescope. NESSY, on the other hand, is installed at the top. Light comes in, hits the primary mirror, it's reflected off the primary mirror and directly reflected into NESSY. That secondary mirror is temporarily removed. And we do this to make our field of view much larger, so we can observe more targets simultaneously. But we have to take this hundreds of pounds instrument from the ground and lift it up in the sky, 110 feet up into the sky, to place it above Palomar and not drop it on this very historically significant telescope. So here's actually some images of the first ever lift test that we had of NESSY. Here is the instrument principal investigator, or PI. This is Michelle Creech-Ekman. She's a professor, PhD at New Mexico Tech. So her and her team built the instrument. I love her shirt she's wearing today, very NESSY appropriate. Here's my boss, Mark Swain at JPL, ignoring me like usual. And what we had to do during this lift test was make sure that NESSY could successfully be lifted off its handling cart on the ground and then lifted over the telescope and its primary mirror. Right about now, we're hoping our insurance policy has started, but luckily it did survive the lift up here, and it did fit inside the prime focus cage as well on the telescope. And here's my boss, Mark. Again, he's not actually smiling. He's really laughing at me because, again, I am the commissioning lead at JPL for NESSY at Palomar. And one of the privileges that I have of doing is having to travel to the top of the telescope to make sure things have been installed correctly and it's working correctly, 110 feet up in the air, which is not the best for someone that is afraid of heights. So he's really laughing at how much I'm freaking out right now. But we get a really cool photo of NESSY installed the prime focus cage on the top of Palomar. And we actually are getting really, really nice observations on Nessie today as well. So I've done some estimates, and we're actually able to get within roughly a factor of 2 of the precision of the Hubble Space Telescope. So if Hubble time and Palomar time, or if Hubble and James Webb time is not available, we still have the capability of making high precision measurements from the ground with instruments and telescopes such as Palomar and Nessie. I'm seeing in the chat a question from Mark is saying that many molecules provide false positives when looking for life. Phosphine is one that does not. Are there others that have found any exoplanets with these molecules? So that's a really great question, and I'll actually come right back to that in a second because I'll be talking about that in a minute. So just sit tight for one more second, because actually what we're really about to talk about right now is how to find life. So this is actually, Mark, your question is actually one of the outstanding questions in the field, is what signature should we be looking for? What sort of molecular bumps and wiggles in the spectra of these planets that we should be looking for that indicate that life exists on these planets? And this is actually one of the outstanding questions, in my opinion, of the field, is what are these signatures or biosignatures, bumps and wiggles that say, if you see this shape in the spectrum of the planet, this indicates that 100% uncertainty that, or 100% certainty that that planet has life on its surface. And it's actually an outstanding question, in my opinion, in the field. And there's actually tons of scientists using, or they're looking into this and researching that right now. There, for example, will have a lab that will have an Earth-like atmosphere, and they'll look at the signal from that planet, and they'll say, huh, this bump and wiggle directly indicates that life exists on the surface of that planet. And you can do other things like make thought experiments, right? We can launch a satellite out into our solar system, and while it's traveling out to the outer reaches of the solar system, we can turn it back to Earth and look at the Earth's spectrum, its signature from its light that it's emitting and reflecting. And we can look for things that might indicate that life exists on its surface. We can look for evidence of oxygen. We have ozone that's produced by plants and algae. We can look for liquid water by looking at the reflectance of light on surfaces of oceans. We can also look for water in the atmospheres of these planets as well. We can also look for signs of biological activity like methane, like cow farts, right? But we have to rule out all other explanations, just as Mark was talking about, right? Just because you have oxygen or water or methane in a planet's atmosphere does not guarantee that life exists on the surface of that planet, because we're finding today water in the atmospheres of many of these planets. We're finding methane. So really the question is what signatures are indicative, without beyond a doubt, that life exists on that surface? And I would argue that that is still a very outstanding question today that will hopefully be answered in the next few years as well. Or alternatively, rather than looking for biosignatures, you can actually try to talk directly with aliens. Voyager 1 and 2, 2 NASA missions that explore the outer solar system, also built here at JPL, which was pretty cool. They had these golden records on board so that if an alien civilization were to find Voyager 1 and 2, they can actually get signs of life from that as well. These 2 golden records have on board many hundreds of recordings of sound on Earth, from waves and winds to also people saying hello in their native languages, also has pictures of and photos and videos of the Earth as well. And on the cover of this golden record, it teaches an alien civilization how to analyze and to look at that record, how to build your own phonograph, how to display the images on your television, and also where the Earth is located, where this spacecraft came from. Similarly, back in the 70s, Frank Drake and Carl Sagan sent messages out to aliens using Arecibo, which at the time was the world's largest telescope. And they beamed this signal out to M13, this globular cluster, and here's the message they sent out, that, hey, we're humans, we think we're kind of smart, we know about counting, we know about molecules and atoms, we discovered DNA, that's pretty cool, that double helix stuff. We sent this message to you guys via this radio called Arecibo, and in case you want to find us, here's where we live. There's the sun, Mercury, Venus, Earth, elevated, because that's where we're from, Mars, Jupiter, Saturn, Uranus, Neptune, and folks, this was the 70s, and they didn't know any better. They have Pluto on this map. We now know today that Pluto is not a planet. That's okay. It's probably for the best, right? Because if there's anything I learned from Independence Day and other alien invasion movies, it's best not to know or let aliens know where you live in some cases. So you can also send messages out to alien life as well. So the question is, where are we now? Well, unfortunately, despite what the History Channel and Ancient Aliens might be telling you, we have yet to make any conclusive detection of extraterrestrial life. And the question is, why not? We now know today that there are at least as many planets as there are stars in the sky. Planets are everywhere, they're ubiquitous. And when there's a lot of planets, perhaps there's also life. But why haven't we found it yet? Well, maybe our technology isn't good enough. I would argue that it wasn't until the advent of the digital camera that allowed us to have the technology to use to discover exoplanets. Or maybe we just haven't found them yet. Maybe they've been talking to us from this side of the sky and we've only been looking over here. Jill Tarter, who's the inspiration for the Jodie Foster character in the movie and book Contact by Carl Sagan, she had a great analogy. If we took the entire universe and shrunk it down into the size of the Earth's oceans, despite of everything we know currently today, we still have only really explored and understand the equivalent of one glass of water's worth. So while we think we know a lot about the universe today, there's still a ton more out there that we have yet to explore, discover, and understand. Or, most depressingly, maybe you're all just alone out there, and maybe life is truly that unique and only exists here on the Earth. Personally, I think life is out there, and it's hopefully only a matter of time, perhaps as soon as the next decade or so before we can find it. But looking to our very strong foundation that's been given to us by amazing work that's been done and is continuing to be done with large and any ground-based telescopes. We've had missions like Hubble, Spitzer, Kepler, TESS, James Webb, a ton of European Space Agency missions that have gone up and are currently being planned and formulated right now. Transformative science is being done all the time today with the James Webb Space Telescope. I know of press releases that are about to come out soon as well. The Nancy Grace Roman Space Telescope that I'm working on personally at JPL, that will be allowing us to learn the technology and the methods that we need to develop and use for future generation missions. And right now, NASA is working on looking at what's next. What's the next NASA flagship mission that will be launched? And the coolest thing about these missions, or this next flagship mission is one of the guiding principles of that is that it must be capable, or that it should be capable of looking at and characterizing small Earth-like planets around solar-type stars, exo-Earths. And perhaps when these missions are launched, hopefully as soon as the 2030s or 2040s, we'll finally be able to answer that age-old question, are we alone in the universe? So with that, thank you so much for your time and happy to take any questions.